Hello, in this video we're going to be talking about differentiability. So we're going to be talking about for a given function and a given point on that curve of the function, is it possible, is it differentiable at that point? Meaning, can we draw a tangent which is not vertical to that curve? And we'll also be talking about how to find the slope of that tangent. So we can denote the derivative. Suppose the function is f of x, and we need to find if it's differentiable at a comma f of a. Then we can denote the derivative at that point as f dash of a, which is given by the formula limit as h tends to 0 of f of a plus h minus f of a whole thing divided by h. And this can be split into two parts, that is the right hand derivative and the left hand derivative. And in the right hand derivative we take the h tends to 0 plus, and in the left hand derivative h tends to 0 minus. So we're also going to talk about how we got these formulae, at least how I would try to derive them. So first of all, we know that the slope of a line joining 2 points, let's just call that m, that is given by the formula m is equal to y2 minus y1 whole thing divided by x2 minus x1. If the points on the line are x2 comma x1 comma y1 and x2 comma y2. So then this is basically nothing but the rise divided by the run, rise over run. Now if we have to find the slope at one point, then it's like we have 2 points, which so it's basically like the x coordinate and the y coordinate are same for 2 different points. So if we just substitute that into the formula for m, so suppose this point is say a comma f of a. So if this point is a comma f of a, and I need to find the slope of the tangent at this point, and if I substitute that into the formula for m, then x1 will be equal to a, and because I'm putting the same point, x2 will equal a as well, and so y1 will equal f of a, and y2 will also equal f of a, because those are the same points. Now if we were to substitute that into the formula for m, we get f of a minus f of a whole thing divided by a minus a, which gives 0 divided by 0, and which isn't really useful here. So the approach to finding the slope at one given point is that we can fix one of these points and then move the other one towards it, and then we can also fix x2 comma y2 and move x1 comma y1 towards it, and see how the value of m changes around when we do that. So for example, suppose the function f of x equals x squared. So first we find the right hand derivative. I mean, we can do it in any order. So one thing is the right hand derivative, which is basically when you fix the left point, so this point here, and then we move this slowly towards a comma f of a. So if we were to just write the value of m over here, we first of all we have here that x1 equals a, so y1 equals f of a, x2 equals a plus h, so then y2 equals f of a plus h. Now if you were to substitute that into the formula for m, we'd get that m is equal to, because it's y2 minus y1 divided by x2 minus x1, we'd get the following, which equals f of a plus h minus f of a whole thing divided by h. Now the idea of finding the derivative, specifically the right hand derivative, is that we fix this point, the left point, in this case a comma f of a, and we move the right point slowly towards the left point on the curve. That is reducing the value of h. So we're taking h really close to 0, we're reducing it to 0. So if we do that, it would look like this. So here we have the formula for we have the graph for y is equal to x squared, and the line is drawn between a comma f of a and a plus h comma f of a plus h. Now if we were to reduce the value of h slowly, and also so if you were to reduce the value of h slowly, we can see that the line joining the 2 points will slowly approach the tangent of the curve at a comma f of a. So if we just directly substitute it, like making h directly 0, then we'd obviously it would be undefined, 0 divided by 0. So that's not really helpful. But if you were to move it really close to it, then it will approach the tangent. So if I were to make this, and the actual tangent of the curve is this pink line, and this yellow line is approaching that tangent as we've reduced the value of h. Now if you were to make this, say, 0.01, then it's really close to the pink line and yellow line are really close to each other. There's still 2 points, but they are much closer to each other. So if we reduce this more and more, then eventually the idea is that the yellow line approaches the tangent line, which is the pink line. So we're basically we are saying that the right hand derivative is equal to the limit as h tends to 0 from the positive side, therefore plus, because we're reducing the value of h. So it was like we started at 1 in this example, so it was 1 and then 0.95, 0.9. So we're coming reducing it from the positive side. So limit as h tends to 0 plus of f of a plus h minus f of a whole thing divided by h. And this is this is how I would derive the formula for this, the right hand derivative. Now for the left hand derivative, it's basically we fix this right point, which I took as a comma f of a, and we move this left point towards the right point on the given curve. So we move a plus h comma f of a plus h towards a comma f of a. So the slope will be equal to here. We can use y1 minus y2 divided by x1 minus x2. It's there's no problem. But okay, suppose x1 equals a plus h, suppose, and so that would imply that y1 equals f of a plus h, and so x2 equals a in this case, which would imply that y2 equals f of a. Now if we use the formula as m equals y2 minus y1 divided by x2 minus x1, and we substitute into this formula, we would get f of a minus f of a plus h divided by a minus a plus h. On simplification, we would get f of a plus h minus f of a whole thing divided by h, which is the same thing as what we got before over here. Now the only difference is that we're taking the limit from the other side, from the left. So over here, suppose we start at -1 and we slowly increase the value of h so that it approaches 0. So if we were to do that, the yellow line again approaches the pink tangent line, and of course that is when h is equal to 0 is undefined, so that's why we're approaching it instead of just substituting the value. And if I were to make this really small, it would be a better approximation for the tangent. The yellow line would be a better approximation of the pink tangent line. So here we have that the left hand derivative equals the limit as h tends to 0 minus, because we're approaching 0 from the negative side. We're increasing the value of h so that it's approaching 0 of, so limit as h tends to 0 minus of f of a plus h minus f of a whole thing divided by h. So which is what we have here. Yeah, now so here we found the right hand derivative as well as the left hand derivative, but so what's the actual need for the two limits? Because from this example we can see that even if we approach it from the positive side, or if we approach it from the negative side, from the right or from the left, then it still approaches the same tangent line. So why do it twice? Why the left hand limit and the right hand limit? Well, suppose the function g of x equals x cubed when x is less than 1, and it equals the square root of x when x is greater than or equal to 1. Then at this point we can see that if we just were to draw a tangent without calculating anything about it, then if we use this curve, the y is equal to x cubed, then at 1 comma 1 we'd get a tangent which should probably look something like this. But if we were to use the curve y is equal to the square root of x and draw the right hand derivative, the slope that we get from the right hand derivative, then the tangent would be something like this. So here we're actually not getting the same tangent line. We're not getting the same slope for the left hand derivative and the right hand derivative. So that's why so to check that, we check both the limits, and even graphically we can see that. So if I were to take the value of h, the right hand limit, then it would approach this line, which looks something like this. And if I were to approach it from the left, then as I increase the value of h, we get a different tangent. So the actual tangents would be these two. So we'd have um, for the when we take the left hand derivative, we get the blue line, and when we take the right hand derivative, we get the slope of the red line. So clearly the slopes are not equal, so therefore we say that this function g of x is not differentiable at 1 comma 1. And by the way, this point, whenever you see a sharp point, it's called a corner, or also a cusp, a corner slash cusp, this point. Anyways, so yeah. Now there is another shorter way to do this. Instead of using the formula each time, like the this method each time, instead of calculating limits, and that is by using differentiation. So differentiability at a point using differentiation. So first, to apply this, first we need to check if the given function is continuous at the given point or not. And if it's continuous, then the given function may be differentiable at the given point. It may or may not be, it's not confirmed yet. But if it's discontinuous, then it's definitely not, the given function is definitely not differentiable at the given point. If it's not if it's discontinuous at the given point. And if it's discontinuous, then we don't even need to check, or don't even need to do step 2. If it's discontinuous, then it's definitely not differentiable. We can conclude that. But if it was continuous, then we check with the derivatives, because even though a function might be continuous, even though a function is continuous, it may or may not be differentiable at that point of continuity. So here we check if the left hand derivative is equal to the right hand derivative at that given point or not, using differentiation. That's the idea with this method. If it is, then the given function is differentiable at the given point. If the left hand derivative is not equal to the right hand derivative, then the given function is not differentiable at the given point. So for example, if you have a function, say f1 of x equals x plus 1 when x is less than or equal to 2, and it's equal to x minus 1 when x is greater than 2. So first of all, this function is discontinuous, as we can see from the graph, or we can just substitute, because the point of interest here is 2, we need to check, so basically we're trying to check if is f1 of x differentiable at x equals 2. So if we want to find that, then we can do this by first checking the continuity, and that's by so if we want to check the continuity, we check that limit as x tends to 0 minus, so this is the left hand, limit, limit as x tends to minus 2 of f1 of x, which is 2 plus 1, which is 3, and we also check the right hand limit, which is limit as x tends to 2 plus of f1 of x, which equals 2 minus 1, which is equal to 1. Now clearly the left hand limit is not equal to the right hand limit, therefore f1 of x is not is not continuous at x is equal to 2, therefore it's definitely not differentiable when x is equal to 2. So now, but what if we proceeded directly with differentiation instead of checking this? Well, if we were to proceed with the differentiation method instead of following step 1, doing step 1, then we get that the left hand derivative using differentiation will be the differentiation of x plus 1 with respect to x, which is equal to 1, and the right hand derivative using differentiation will get that that's equal to the differentiation of x minus 1 with respect to x, which is also equal to 1. So here the left hand derivative looks like it is equal to the right hand derivative. So with what we did before, if it's equal, then it's supposed to be differentiable, but that's where this if we do this directly, this method doesn't work. That's why I have to check the continuity. So but if we apply the limits, then that would definitely work properly. We don't have to check the continuity again if we apply the limits. So the left hand derivative equals a limit as h tends to 0 minus of f of, here it's 2 plus h minus f of 2 divided by h, which is equal to the limit as h tends to 0 of 0 minus of. So here f of 2 plus h, if we are taking h tends to 0 minus, that means that we are having values like say minus 1, minus 0.9, minus 0.8, and so on, up until we were approaching 0. So this is so the value of h here is negative. So 2 plus h, because h is negative, we get that 2 plus h will be less than 2. So that's why we use this function here. We substitute this function x plus 1. So we get 2 plus h plus 1. So here this is the value of h, 2 plus h. I mean that's the value of x that we're substituting, 2 plus h minus f of 2. F of 2 we were already given in the question that when x is equal to 2 we use x plus 1, because that's when x is less than or equal to 2. So we substitute that. So f of 2 will be x plus 1, right? So that would be 2 plus 1 divided by h, which equals that's equal to limit as h tends to 0 of 0 minus of 1, which is just 1. Now to find the right hand limit, suppose we have to find now we have to find the right hand limit. So that's the limit as h tends to 0 plus of f of 2 plus h minus f of 2 whole thing divided by h, which is equal to the limit as h tends to 0 plus of limit. So here, because we're having h tends to 0 plus, so it's like we're approaching 0 from the positive side. So like in the previous example we took it from 1, so we had 1, 0 0.95, 0 0.9, and so on up until we were approaching 0. So here h is positive. So because h is positive, that would imply that 2 plus h is greater than 2. So that means that we need to use this one, x minus 1, we need to substitute that. So here in the place of x we substitute 2 plus h, and we substitute minus 1 minus f of 2. F of 2 is still x plus 1, so 2 plus 1 whole thing divided by h, which is the limit as h tends to 0 plus of h plus 1 minus 3 divided by h, which is equal to limit as h tends to 0 plus of 1 minus 2 by h, 1 minus 2 by h. So that can be written as, so basically if we split the limit, then if we distribute the limit we get this. So now as h tends to 0 plus, 2 by h is going to approach infinity. So 1 minus whatever's approaching infinity, this will approach minus infinity, which is clearly not the same as the left hand limit. So the left hand derivative, so the right hand derivative does not equal the left hand derivative does not equal the right hand derivative. So therefore the given function is not differentiable when x is equal to 2. So basically we can see from this that if we go with this method, then we can, although it's much longer, we were still able to get the correct answer without checking the continuity. But if we can check the continuity, then we might be able to confirm it with just that. So in this example we have f2 of x equals 3 minus x when x is less than 1, and it's equal to 2 divided by x when x is greater than or equal to 1. So if we use the limits method, so we can first calculate the left hand derivative, which is equal to, so here we have to find the is it differentiable at x is equal to 1. Suppose that's what we have to find. So with the limits method we get f of 1 plus a limit as h tends to 0 minus of f of 1 plus h minus f of 1 divided by h, which is the limit as h tends to 0 minus of, so f of 1 plus h. So because here h is less than 0, which implies that 1 plus h is less than 1, we use this we substitute 3 minus x squared, and here x is equal to 1 plus h. So we get this minus f of 1. F of 1 is already given as 2 divided by x, so we get 2 divided by 1 whole thing divided by h, which is equal to the limit as h tends to 0 minus of 1 minus h squared plus 2h plus 1 whole thing divided by h, which is equal to the limit as h tends to 0 minus of minus h squared plus 2h whole thing divided by h, which is equal to the limit. So here we can cancel the h because we're just approaching h is equal to 0 minus, it's not actually 0, so we are allowed to cancel the h's if we choose to. So here we can write this as this, and now we can just substitute 0 into in the place of h. So we get minus 0 minus 2, minus of 0 minus 2, which is minus of 0 plus 2, which is minus 2. Now for the right hand derivative, we can have the limit as h tends to 0 plus of f of 1 plus h minus f of 1 whole thing divided by h, which is the limit as h tends to 0 plus. Now here h is greater than 0, which implies that 1 plus h is greater than 1. So we use this form, which is 2 divided by x. So here in the place of x we're substituting 1 plus h. So we have 2 divided by 1 plus h minus f of 1. F of 1 is already given as 2 divided by x, so we take 2 and in the place of x we substitute 1, and we whole thing divided by h, which is equal to the limit as h tends to 0 plus of so here we can take the 2 common, and we have 1 over 1 plus h minus 1 divided by whole thing divided by h. So here we can take the 2 out of the limit, or it's basically like distributing the limit of minus h divided by 1 plus h times h. So which is equal to 2 times the limit. As so now it's h is not actually 0, even though later we're going to substitute it as 0. So here we can cancel the h's, and we'd end up with this. And now we can substitute h is equal to 0. In the place of h we can substitute 0. So we don't need the limit anymore. So we'd have minus 1 over 1 plus 0, which is equal to minus 2. So here the left hand derivative does equal the right hand derivative. Therefore the given function, that is f2 of x, is differentiable at x is equal to 1. Now we can also do this with the differentiation method, but for that first we have to check the continuity. So to do that we can find the left hand limit, which is so the left hand limit is limit as x tends to 1 minus of 3 minus x squared, because h is less, we're starting from a when x is less than 1, so we have to take 3 minus x squared, which is equal to so for this we don't need to simplify this or anything. You can just substitute the value of x as 1, and then this would be equal to 2. The right hand limit is equal to limit as h tends to 1 plus of 2 divided by x, which is and even here we can just substitute the value of x, and that would also give us 2. Now f of f2 of 2 no f2 of 1, if we see the value of that, so basically we're just substituting that into the formula, I mean into the equation that's given, we'd get 2 divided by 1, because this can be taken when x is equal to 1 as well. So we'd get 2 divided by 1, which is equal to 2. Now because the left hand limit equals the right hand limit, which also equals the f2 of 1, we can say that this function is continuous when x is equal to 1. Now so we can differentiate it and check what we get from the left and the right, and then if those are equal, then it's differentiable. So this was step 1. So now for step 2, so because it's continuous, we can proceed with the second step. So the left hand derivative equals the derivative of 3 minus x squared with respect to x, which equals 2 times x, and we're interested in the point when x is equal to 1, so that would be 2 times 1, which is equal to 2. The right hand derivative is equal to the differential of 2 divided by x with respect to x, which equals minus 2 divided by x squared, which is and when we substitute 1, we get 2 divided by 1 squared, which is equal to, wait, what? Oh, okay, wait, this is supposed to be minus, so the differentiation of 3 minus x squared with respect to x is minus 2x, which is minus 2 times 1, which is minus 2, and the right hand derivative is the differentiation of 2 divided by x with respect to x, which is minus 2 divided by x squared, which is minus, and we substitute 1 in the place of x, and so we get minus 2. So now because both the differential both the both the like both things give us the same answer, we can conclude that this function is indeed differentiable when x equals 1.